next property is very straightforward. It's called change of scale. It's just basically if you have a Laplace transform of a function f, but now instead of just the argument, you multiply a and b. So basically changing the argument t by a constant factor. Okay, so that you can figure out the property by just plug in the formula, the definition of Laplace transform, right? E and f of at dt. And basically, we define your variable. You call that, you change that to t, or you call it like a new variable, t pi, right? E minus s. The f, this change to t pi. So t pi is a times t, so t is t pi over a, right? And dt will be dt pi over a, right? And now this, other than this factor a, this is still the formula of Laplace transform, except s also changed. So this should be a new s over a is a new s, right? And other than this thing, so it's 1 over a. The rest is just Laplace transform of, or we can say that the Laplace transform f is what we call the little f, right? And little f depends on s, but now it depends on s over a. Right? Very straightforward. Is that okay? So it just helps you. Sometimes you don't have the transform or the function exactly of the same of the form that in the tables. Is by factors, that this will allow you to change, get transformed in a straightforward manner without exactly the same in the lookup table. Okay. The next one is also familiar. There's something similar in Laplace transform, but I don't think a textbook talk about it. But people doing Laplace transform, I mean Fourier transform is very familiar with that one. So it's the textbook called substitution is more like a translation of the transform variable. So again, you have this. So basically, write down the definition. Fs is Laplace transform of Fd, right? That's the usual definition. Now you just shift it to a translation of the transform variable as minus a in the textbook, right? Minus a. Where you just again do a plug in the definitions of infinity e to the minus s. Now the s is changed, right? This becomes s minus e. Right, and that becomes pretty straightforward. Just again, a change of variable, right? You call that I mean, it's not exactly a change of variable. It's just that you know, multiplying this out, so either minus st and then f exponential function at and f d dt. So that by definition is just the Laplace transform of e to the at. Yeah. That's almost nothing, but it's just saying that if you translate the transform variable, whatever the inverse transform, the original function, it's just you multiply by exponential factor, right? And the exponential is depends on how much you translate it. So minus a becomes at. Right. And, all right. Yeah.
Also,
Say that again. I don't. Yeah, seems like it's just saying that you have a transform, Laplace transform that you saw. That is not exactly the form of your standard table, but it's like the one of the entry with a translation in the transform variable. Then you just look up whatever the transform that corresponding to that one and multiply by the exponential function. So you don't need an independent item for this shifted transform. Wherever you shift it, it's just multiplied by exponential function. Right? Does that answer your question? I'm saying that, I mean, the Fourier transform is just, we also have the similar situation. Sometimes you have a Fourier transform, you just shift the omega, shift the frequency by a little bit, and all it does is that it's like you multiply the function by a phase, by sinusoidal function. In that case, it's not the exponential function, it's either the I omega t, whatever you shift the frequency. Either depends on your convention, either I omega t or minus I omega. Right? That's a familiar property in Fourier transform anyway. But the Laplace transform have something similar. And I mean, although it's trivial, looks like trivial, but it saves your time in figuring out. Like we'll use that in the next example, and once you have that, it's come in quite handy when you are getting, like, you try to get an inverse transform, but your transform actually it's not exactly the standard form, but a shifted one. And you just look that up and you get the exponential function out. Is that okay? So that I mean, as a useful formula. Without formula, you just need to redo everything. It's not very difficult. You can still do it. Is that okay? So, right. So we apply this to the next example. And the next example is a dam oscillator. Probably you have done the dam oscillator somewhere. I don't know whether it's that general physics or the upper level mechanics or something like that. But anyway, you've probably seen that before, but we are solving it now by Laplace transform. Okay, and it's just a little bit more math. It's nothing to you just have to be patient and not getting error. Okay, not because of all this. There's just more math. It's nothing. Okay, yeah. So the equations, x double prime means second derivative in time. This is the acceleration, and our mass is the force. And there's extra term proportional to x prime, which is turns out to be a damping term. Okay, it's always of t, and then I think the k has the physical meaning of a spring constant, something like that. And it's homogeneous. Later on, there will be an example or inhomogeneous one with a driving term. But now this is homogeneous. We solve that subject to initial condition. At t equals 0 is x sub 0. And x prime 0 is 0. All right, so that's the second term is different from the other example that we did with just a simple harmonic oscillator adding a damping term. And I mean, just like the other example, you can solve it by Fourier transform also. But solving by Laplace transform, has some advantage because you are basically substituting the initial condition while you are solving it. So you don't, when you solve Fourier transform, you usually write down the general solution and just plug in the initial condition and solve for the coefficient. And you can still get exactly the same solution. It just depends on your choice, which one you think is easier. Okay, then now you do the Laplace transform for each term, and we did that before. So the first one is second derivative. So you have by the formula, the first one is s squared. S squared, the transform of capital X, I think your textbook called little x. And then minus s times the function itself, right? X at 0. X, capital X now at 0. And then supposedly you minus x prime 0 also, but x prime 0 is 0, right? Yeah, so that is for the first term. And the second term is the same. You have one derivative, so you s times x and minus the initial condition, which is x of 0, which is just that this is also x of 0. So you can just directly substitute x of 0. Okay. And the final one is just direct Laplace transform. Right. And now this is just an algebraic equation for little x. So you solve for little x. X is put everything that not depends on x on to the other side. The other m, and both depends on x of 0. So m times s, and then b. So it's m s plus b x of 0. Right, and the denominator is summing all the coefficients, m s squared, and then plus bs plus k. Right? Hopefully I got it right. ms squared, yeah, right. Right. So now the task is just to get the inverse transform because you already substituted the initial conditions. So that when already satisfy the initial conditions, once you solve the inverse transform, you get the solution. And now you compare with your lookup table, and nothing is exactly the same. So, but you recognize the second order. So the one way to do it is do the complete square of that one, because all the formula mostly involving s squared plus something or minus something. Right? If you go back to your table, right? So and the numerator is fine because it's linear. So you have some item have that proportion to s, some proportion is just a constant. So the task is to do a complete square of the denominator. And to do that, the first thing you can do is divide everything by m, right? Because you want the s, you just want to have s squared, something similar to s squared, right? Or s minus something squared. So dividing that, so that becomes s plus p over s, p over m. And this is s squared plus p over s over m plus k over m, right? And now you do the complete square of the denominator, which I assume you know how to do it, right? So the complete square. I think I did in another example. I did that. So you have s you want to s plus something square, and you keep that first, k over m. This doesn't involve in the complete square. And you want to have a linear term in bs over m. And so it has a factor of 2. And so it must be b over 2m, right? And then it's positive sign, right? That would make the middle term 2s times this one, which is sb over m. So this one, right? And so if you do this, you have you add the square term. You need to subtract the square term, right? Minus b squared over 4m squared. Okay, so not too bad. So now you got something that almost the same, but you realize that now this is your new s. This is like a translate, just use the translate formula. Just translate s to s plus b over m, but the numerator s plus b over m, not to b over 2m. So you probably want to separate in the two terms also. This is 2m plus another b over 2m. Right. Then you separate this. One term is this one divided by the denominator, and then the other is just a constant divided by this, the same denominator. Okay, so that's, you got two terms. And another convenience, because more formula, the second one is a square term, so you define a square term, define a new variable that is square of that. We call that, I think the text will call it, what do you call it? B over m over b square. Omega 1 square is defined because it has the dimension of frequency square. It's omega 1 square, right? Right, so that is almost done. So now you look up your table. That go back to the table. So now so this is like s squared plus k squared item, right? And if you have an s, then you get a cosine. S divided s squared plus k squared, you get cosine kt. If k divided by s squared plus k squared, you get sine of kt, sine kt, right? So that that's to be explicit, just write it. So the Laplace transform of cosine kt is s divided by s squared plus k, s squared plus k squared, plus transform of sine kt, k divided by s squared plus k squared. Okay, just write it down so that you can do a comparison, right? So this one divided by this one is like that, so you have cosine, but then you shift the transform variable, which means the inverse transfer you multiply by the exponential function of the shift. But the shift is defined as minus, so the exponential function of the minus of this one, right? So x now is the inverse transform of x. Now the first term is just, you have the x0 is the overall coefficient in front, so that doesn't involve. And then the first one is just exponential function minus b over 2mt coming from this shift, right? And then the cosine, cosine. And k is this one, because comparing this is k squared, this is omega 1 squared, so it's omega 1 b. Oh, so that's the first term. The second term is a constant. but you want to make it like a k, which is omega 1. So you multiply by omega 1 divided by omega 1, right? So both has the same coefficient, so you might get the exponential function out, right? The second term has you multiply omega 1 divided by omega 1, so b over 2m omega sub 1, and that one is a sine omega 1t. Right. That should be the answer. Right. Let's look at that. All right, so that is the answer. I mean, that is a good enough final answer, but the last line is just make it look nicer. It's nothing actually. Just combining the two terms and make it a phase. You do it is just write it as a tangent. This is I think it's a tangent phi. Right there. Let's find some space to work on that. Just basically define tangent phi as b over 2m omega sub 1. Okay. So that becomes a tangent, which is sine and cosine, sine divided by cosine, right? And then you get the common denominator of cosine out. That becomes cosine omega 1t cosine phi plus sine phi sine omega 1t, which use the formula, addition formula of sine cosine function is cosine omega 1t minus phi, right? If you do remember the formula. But you divide it by the cosine overall. But you figure out the cosine. The tangent phi is like that. You figure out what the cosine phi is. The tangent phi is like that. It's like you divide b over 2m and then divided by omega 1. And this one is square root of omega 1 square plus b over 2m square. But you substitute the definition of omega 1 square. Omega 1 square is k over m minus b square over 4m square, which is exactly this one. We subtract that, so this becomes k over m square, and then take the square, so this actually just k over m. I think this you can define as omega sub 0, the square root of that. So this one is square k over m minus this one. This is omega sub 0. The cosine of omega sub 0 is the original frequency without the damping. The oscillation frequency of the oscillator is just usual square root of k over m. The cosine phi is omega sub 1 over omega sub 0. Okay, so you just now combine everything, x0, and then divided by cosine, meaning you are multiplied by omega sub 0 divided by omega sub 1. And the rest is the exponential decay and the cosine with the phase. Okay, so I think that is the last answer. It's okay, so not too long. It's just have to have patience to get everything done systematically. It's okay. I'm going through that at least one time. A calm question is just asking you to do it exactly the same problem, right? Using Laplace transform. So we just get on with it and use all the formula. I mean, hopefully, and I don't know whether that question gives you all the transform. If you don't have this transform, you need to redefine. You rederive all the transform, which is straightforward. We did those examples before, right? And also this translation formula, getting the exponential function. If you don't have that, just figure out, you shift the transform by a certain amount, what would you get from the inverse transform. You just rederive the equation if that is not given to you. Okay. Right. All right. So that's the example. Any question about